Bismillahirrahmanirrahim. Assalamu alaikum students. Today we will discuss nonlinear elasticity. In the previous video we have discussed plasticity and completed the plasticity topic. So today let's start the nonlinear elasticity topic. Nonlinear stress strain behavior. Generally when we see metals we have two main regions, elastic and plastic region. The elastic region for metal is generally a straight line and plastic region is generally nonlinear. But there are few materials in which the stress strain diagram is nonlinear even in the elastic range. So this nonlinear elasticity are basically related to those materials. Now stress strain behavior for metals gives linear relationship till yield point, later exhibits non-linear plastic deformation region. But many materials when loaded gives complete non-linear stress strain behavior. Polymers such as rubbers, elastomers are generally possessing non-linear stress strain behavior. So the examples are rubbers and elastomers. So we can see the stress strain diagram of rubbers. It is totally non-linear. Okay, generally it's an elastic material and it shows total nonlinear curve. Young's modulus for materials exhibit nonlinear stress strain behavior can be determined by dividing complete curve into small divisions such that each portion will be a straight line. We know that now the curve is total nonlinear and material is basically behave elastically. So if you want to calculate the Young's modulus, and as we know that Young's modulus is the slope of a straight line, okay, so what we do, we basically divide our complete stress strain curve into small element such that each element is almost linear. Then we add all of them and divide with the number of elements, so we get the Young's modulus for that particular material. So addition of all the values and dividing by number of divisions will give the value of Young's modulus. Okay. Another approach which can be used to determine Young's modulus for nonlinear elastic material is based on the theory given by Ghent in 1996. So Ghent basically proposed that by closely looking at the stress strain behavior of rubber-like materials, he found that at initial deformation, the material can be approximated to a straight line. Although it is not 100% a straight line, but it is giving us 95% or more, match with the straight line. Okay, or fitting with the straight line. So Ghent determined the elastic modulus by considering only 10% data of the total stress strain curve, where the curve is almost linear. Okay, so I hope you understand that instead of taking the complete curve, what actually the Ghent basically did, he just took the initial 10% of the data and then try to fit a straight line on that curve. Then what he get almost 95 or above basically the match, and then he determine the slope of that straight line, and then he compare the value of that Young's modulus with the by considering the complete curve, and when he compare he found that he got the better match of Young's modulus. So it is one of the method by which we can determine the Young's modulus for rubber like materials. So he compared elastic modulus for many rubbers, found that by both techniques the values are very near. Hence, it is recommended to use only 10% data of a stress strain curve to determine Young's modulus. So now the first heading is related to the Young's modulus of nonlinear elasticity, and I hope now you understand that there are two approaches. First, divide the whole curve into small linear elements and then determine the slope, and then add all these slopes and divide with the number of elements. We get the Young's modulus. And the second approach is use initial 10% data and then determine the fit the straight line and determine the slope of that straight line will give you the Young's modulus. Now, material models for rubber-like materials. So what are material models? Generally, when we apply load on any material, it shows some sort of behavior, and those behaviors are different for different type of materials. Even for metals, they are different behavior, and for polymers, the behavior is different. Like for plastics and rubbers, they behave differently. Okay, so material model is basically the equation or mathematical equation that basically defines the behavior of a material. Okay, elastomer can be treated as a hyperelastic material, commonly modeled as incompressible, that is, the volume will not change, homogeneous, isotropic, and non-linear elastic solid. Okay, non-linearity we have seen in the previous diagram that it's totally non-linear. Isotropic, the properties are assumed to be similar in all directions, and it is homogeneous and generally incompressible. But there are few material models that basically include compressibility also. Okay, so but generally these materials are behave incompressibly. So most of the material models follow incompressible material. Due to long and flexible structure of elastomers, it has the ability to stretch several times its initial length. Now you have seen this, that when you stretch a rubber, okay, it will elongate more than its length. Sometimes 700% elongation is there, and when you remove the load, it will come back to the original point. Okay, elastomers at small strains up to 10% have linear stress strain relationship, or we can say almost linear stress strain relationship, and behave like other elastic materials. In case of applications where large deformation exists, means what we are saying large deformation means more than 10% deformation is there. Okay, the theory of large elastic deformation should be considered. That is, we cannot consider them as linear. We have to consider them as non-linear. Several theories for large elastic deformation have been developed for hyperelastic materials based on strain energy density function. So now what is hyperelastic? Generally, elastomers or rubbers are considered as hyperelastic because they have large stretchability. They can stretch up to larger extent. Okay, that's why they call hyperelastic materials. And strain energy density function, basically the material model is basically derived that when we apply load, we have a strain, and there is some amount of energy that is stored. So when we remove the load, so energy come back and the material will regain its original position. So that is the strain energy density function. So all rubber like materials, basically the material model or the deformation behavior is basically defined by strain energy density functions. Now, important inputs for analyzing these materials are the selection of strain energy potential, okay, and the determination of material coefficient. So these are the two main challenges. Okay, first, that how to develop the strain energy potential. Okay, because in rubbers also based on cross linking, the behavior is totally different. Okay, so we have different strain energy potential for that. And also the second challenge is the determination of material coefficients. Okay, generally we need some coefficients in material models. Okay, so those coefficients are basically based on the material properties, but sometimes it's very tough to determine the coefficient. But these are the two main challenges. Okay, now different mathematical models have been suggested for the prediction of stress strain behavior in elastomeric material, that is different material models you can say. Okay, for predicting the stress strain relationship or the behavior of a material. Rubber elasticity theory explains the mechanical properties of rubber in terms of its molecular constitution. So, rubbers are different than the metals. So, generally, rubbers are formed by the chains. It has chains So the theory which defines the material models are generally follows the molecular constitution, that is in terms of the chains. So that's why for rubber-like materials we have single chain, multiple chain, okay, 3 chain, 8 chain models, okay, material models. Now first, a statistical mechanics approach to describe the force on a deforming elastomer network assumed Gaussian statistics. Okay, so first basic material model is follows Gaussian statistics, which assumes that a chain never approaches its fully extended length. As I have explained that rubbers are made up of chains. So when we apply the load, the chains will stretch. Okay. So Gaussian statistics assume that when the load is applied, chain will never approach the 100% extensibility. Okay. Means we don't have large deformation. We have only deformation of a small level. Okay. So that is Gaussian statistic in which chain is not reached the fully extended length. Researchers also suggested material models based on non-Gaussian statistics. We know that in reality, when we apply load, we generally have large deformations, or the rubbers has large, large deformations. So it's better, or the better material model is non-Gaussian based, in which the chain can approach the fully extended length. So the distinctive features of non-Gaussian approach is that it presumes that a chain can attain its fully extended length. Okay, so it is a difference. Gaussian, the chain will not reach the maximum length, maximum stretchability, but in non-Gaussian, the chain can reach the maximum extensibility, okay, or the maximum stretch. These are physical models based on an explanation of a molecular chain network. Now there are another type of material model, that is phenomena based, phenomenological invariant based, okay, and stretch based continuum mechanics approach. So three types of material model. One is molecular chain networks, in which we assume different number of chains. Second, phenomena invariant based, and you know that we have a stress invariant, strain invariant. So when we apply load, so how it behaves. So based on that, in terms of invariant, we have material model. In that material model, we have invariants as a variable. Okay, it means I1, I2, I3 are present in that equation, and then stretch based. And what is stretch? We have generally studied the strain. Okay, so if LF upon L naught is a stretch, so stretch based continuum mechanics approach is also present there. We have three types of material models, or three classes of material models. Okay, a hyperelastic material model is a type of constitutive relation for rubber like material. Now you know that constitutive relationship is something in which stress is related with strain. So we are talking about that hyperelastic material model is a type of constitutive relationship for rubber like materials, in which the stress strain relationship is developed from a function, and that function is strain energy function generally. Okay. Figure below gives a classification of different types of hyperelastic material models. As I have explained in the previous slide, that we have three types. Okay, molecular uh, chains type, phenomena based, and third is stretch based. Okay, so now micromechanical type, that is chain type, we have 3 chain, 4 chain, 8 chain, full chain. These are few examples, and the name are, let's say, 8 chain model is a very famous model for rubber like material, is Aruda Boyce model. The name famous is, the name is basically Aruda Boyce, and generally it's also known as 8 chain material model. Now, phenomena based we divide into stretch based and invariant based. The only difference is that in stretch based we have stretch as a function, a variable, and or the property, and invariant based we have invariant as a property. So stretch based we have one example, Ogden. Okay, in invariant base, there are many different examples: Newton, Muller-Evelyn, Van der Waals, Ghent, Yu, Marlowe. Okay, so these are the classifications of hyperelastic material model. You don't need to memorize them, but just for understanding, just keep in mind that they are stretch based, they are invariant based, and they are micromechanical. Okay, okay, and if you remember previously we have discussed Gaussian and non-Gaussian. So out of them, all of them are non-Gaussian except New-Hawkian. New-Hawkian is the only Gaussian statistics based material model. Okay, so that classification is another classification. Okay, so we have already established or discussed that in the previous slides. So I hope you understand that what do we mean by material models and what are the examples of material models of rubber-like materials. Okay, so let's move to the next heading. Now, structural behavior for rubber-like materials. As I've explained that rubbers are comprises of chains, and natural rubbers generally have no cross links. Okay, chains, you know that chains means like a thread. Okay, we have multiple chains or multiple threads inside the rubbers. Okay, and natural rubbers have these chains, but they have no cross links. Acha, what do we mean by cross links? Cross links are basically the chemical bond. Now take the example of a noodle, for example. You know, if you see take a cook noodles, so they have the link with each other. But when you try to stretch them with your both hands, what happened? They will straighten up, and they have physical sort of entanglement. Okay, but if you see that if you combine those chains with some chemical bond, then that chemical bond is known as cross links. Okay, so natural rubbers don't have cross links, and if the material has no cross links, means it's a weaker material because you cannot use that material in any applications. So what basically we do, we take natural rubber and we apply some chemical processes, like we add some sulfur in it, by which by adding sulfur we develop or create a chemical bond, that is a cross link. So that makes the elastomer more stronger, or the rubber is known as now vulcanized rubber. Okay, so I hope you understand this. You, for example, take the example of chewing gum. So if you stretch the chewing gum, it will break. Okay, at very small load. So, but if that rubber has basically we add sulfur in it, so chemical bond is there. So it will produce cross links. So that rubber is called vulcanized rubber, and by which the strength is improved. Now the vulcanized rubbers generally possesses higher strength as compared to natural rubber because more energy is required to break cross links. Okay, rubbers generally have two types of entanglements: physical and chemical. Okay, physical means they are just sliding on each other. Okay, that I have given the example of noodles that they are sliding on each other. Second is chemical, that is there is a bond, chemical bond in between. Okay, that is cross link. So now see this diagram. Okay, in this diagram you can see that these chains are just have physical entanglement, that is they are sliding on each other. But these are the chemical bonds. Okay, we can see. So these are the cross links. Okay. So natural rubbers have no cross links like this. Okay, no chemical bond. So they have only slides on each other that are having the physical entanglement. That's why when we stretch those rubbers, they will break at a smaller load. Okay. On stretching the chains, they become straight and slide on each other. More load will result in breaking of chemical entanglement, that is cross links. Now, for example, take this elastomer, and as we assume that we have cross links, so when we stretch them, they become straighten up, and now we can see the load is on the cross links. Okay, when we further up, increase the load, what happened? These cross links will break, and then at the end we have the rupture of the rubber. Okay. So, which is more stronger, natural or vulcanized rubber? Of course, vulcanized rubber is more stronger. Why? Natural rubber has no cross links and have only physical type of entanglement. On the other hand, vulcanized rubber has cross links. So, due to the presence of cross links, vulcanized rubbers require more load to fracture as compared to natural rubber. Why? When we apply load on natural rubber, what happened? The chain gets straight, and then when we increase the load, the chain start breaking because there is no chemical bond. So this will occur at smaller load, and at the end, the rubber will rupture into two parts. But on the other hand, vulcanized rubber that have cross links, when we apply load on that, they will try to straighten up, and then the load will be on the cross links. So when we increase the load, the cross-link or chemical bond will break. So when the chemical bond will break, after that the chains start breaking. Okay, and then we have the rupture. So cross-links will take more load and require more energy to break. Okay, so that it will prove that vulcanized rubber has more require more energy or having more strength. Under the load, vulcanized rubber first stretches and then the crosslink resists the deformation. Vulcanized rubber does not fail unless the crosslinks are broken. Okay, so crosslink will broke and then change is broke and then ultimately the rubber will rupture into two parts. Now chain density. For any rubber-like material, network strands are formed both by cross-linking and physical entanglements. So what do you know chain density? So what are the number of chains present inside the rubber? And we found that the it's a huge number. They are 10 is to 20 or 23. Okay, chains in a rubber material. Okay. As the degree of cross-linking increases, the cross-link chain density increases. Okay, now what is this? You know what? When we say a chain means the link between the two chemical bonds is one chain. So if you increase the cross-links, so what happened? The smaller portion or the smaller links will increase. So it will increase the chain density. Okay. So when the crosslinks increases, the chain density automatically increases. Now that makes the elastomer more rigid, thus giving higher values of stiffness and shear modulus. More crosslinks, more energy is required to break that material. For elastomers subjected to small strains, shear modulus is directly related to the number of crosslinks chains per unit volume (NC). So this is a very famous relationship that is basically given by Taylor in 1975. So that is G is equal to NCKT. Okay, NC is number of chain or chain density, K is Boltzmann constant, and T is absolute temperature in Kelvin. Okay, and G is the shear modulus. Now this is very important formula. Whenever two domains are mapping up at a single point, then the formula becomes very important. For example, when you transform what you call it, the Cartesian into polar, the equations are very important. Similarly here, the mechanical property is related to the chain molecular property. Okay, so that is why this formula is very important. So where K is the Boltzmann constant and T is the temperature in kelvins. So I hope you understand this formula. G is equal to NCKT, where G is the shear modulus and the unit is megapascal or generally Pascal. Now number average chain molecular weight, or generally it is known as molecular weight. Length of network chains decreases due to an increase in the degree of cross-linking. Okay, I have explained this in the previous slide. In any polymer, chain density is closely related to the average molecular weight, and this property can also be used to explain the mechanics or deformation of rubber-like material. When we see the micromechanical models, we found that molecular weight is very important. Okay, so now this heading in this heading basically we try to drive the relationship for molecular weight in terms of the shear modulus, okay, or modulus of rigidity. Now multiplying and dividing equation by Avogadro's number Na and recalling that R is equal to NaK. So we can obtain this relationship. We know that Nc is equal to Kt. So when we multiply with Na and divide with Na, so Nak will replace by R. So the new relationship is G is equal to Nc RT upon Na, where Na is the Avogadro's number. If n is the number of chains, Avogadro's number can also be written as, by the basic definition of Avogadro number, we can write that Na, the Avogadro number is equal to n times mc, the molecular weight, divided by the mass, particular mass. Okay, so this is the another relationship. Na is equal to n mc upon m, and we derive this by the basic definition of Avogadro's number. Also, combining definition of chain density, that is Nc is equal to number of chains per unit volume, with equation 1 yields. Now Na is equal to nmc upon m, we have derived in the previous slide. So if we use n is equal to nc times v, so we replace n with nc times v. So we have nc mc v upon m. So V upon m is basically m upon V is density. So we have rho. So NC MC upon rho. So when we rearrange, we get NC upon NA is equal to rho upon MC. Okay, so this is equation number 4. Okay, how we get this? We replace n from this equation. So small n will be NC times V. So when we put NC times V here, so we get NC MC V upon M. And V upon M is basically 1 upon density of simply density. So we just replace rho here. So we get NC MC upon rho is equal to NA. So rearrange, we get this relationship. Comparing this result with equation 2, we can get the expression for the number average chain molecular weight. Now this is the equation 2, G is equal to NC RT upon NA. Now if we compare these two, okay, so we get NC upon NA is equal to rho upon MC. So we just replace rho over MC, okay, and we can solve for MC, that is MC is equal to rho RT upon G. So this is the relationship for the molecular weight, again in terms of the shear modulus, and we additional property that is required is the uh, density of the rubber or polymer. Okay, once the values of shear modulus is determined, these structural properties of elastomers NC MC can be easily evaluated using equations 1 and 5. Okay, so this is 5 and 1 is NC KT. So now I hope you understand the derivation of molecular weight. Now just we'll solve one numerical. Rubber has an average chain density of 2.73 10 to the 27 meter square kilogram per second square, and density of 1.2 10 to the 3 kilogram per meter cube. Rho is also given, NC is given, okay, and at 310 Kelvin temperature is given. Now determine the shear modulus and molecular weight. Okay, so we have to determine these two properties, and given conditions are that Boltzmann constant is given, okay, that is 1.38 10 to the minus 23, and our general gas constant is given 8.314 kilogram meter square per Kelvin per mole second square, okay, per second square. Okay, so you got these two properties, and we know we have NC, we have rho, and we have T. So now let's see the solution. Since we know G is equal to NCKT, so just replace NC, that is 2.73 10 to the 27, K 1.38 10 to the minus 23, and T is 110. So we got G equal to this. So we simplify and solve. We get 11.67 megapascal. Okay. So now if you see the what you call it, the units, okay, megapascal. So you will find that many will be cancelled out, and uh, by using the equation of formula of Newton, we can simplify and get this relationship G. Okay, so if chain density unit is meter square kilogram per second square, and Boltzmann in this unit we always get megapascal, and in the problems, other problems also, the unit remains the same. Okay, we will not change the units. Okay, now the second part is molecular weight. So we know the formula rho RT upon G, and just replacing the values here. Rho is 1.2 times to the 3, 8.314, 310, and G is we have calculated here 11.67 times to the 6. By solving it, we get MC, that is kilogram per mole. The important thing is the unit of R. The R general gas constant can be written in different units, okay, but we always use this unit kilogram meter square per Kelvin per mole per second square, so that we get kilogram per mole. Okay, so and if R is given, it always be given in this unit. Okay, so you automatically get kilogram per mole. Thus you have to memorize that the unit should be the same, and I will if I give the numericals, the K and R will be in the same unit, and NC again in the same unit. So I hope you understand these two numericals, okay, G for G and NC, and I hope you can determine these properties if uh, NC is given to you, and density is given, and temperature is given, and K and R are the general constants. Okay, now uniaxial tension test for incompressible hyperelastic materials. Rubber-like materials, hyperelastic materials is under uniaxial tensile load as shown in figure below. Now see, this is a element in which generally initially it's a cube. When we apply the load in one direction, uniaxial tension, so the length will increase. Okay, and what happened to the other dimensions? Okay, if we assume a cube, the deformation in height and width will be same. Okay, so when we apply the uniaxial load, the length increases, height will decrease and width will decrease. Load will elongate the body in axial direction, while other two lateral directions it exhibits reduction in width and height. Okay, so this is you already know. Now material is assumed to be incompressible, hence volume remain conserved. So we have said that that these materials are generally followed that they are incompressible. So when we say incompressible, the volume before and after remains same. So Vf is equal to V naught, that the final volume is equal to initial volume. So if we simply convert that in terms of the thickness, width, and length, so final volume is equal to initial volume. And when we take, and also we know that strain is equal to change in length of original length, and we can write strain LF minus L naught upon L naught. And if we take LCM break, we get epsilon is equal to LF upon L naught minus 1. So epsilon plus 1 is equal to lambda, and lambda is LF1 upon L naught. So if we divide these two, okay, LF upon L naught, WF upon W naught, TF upon T naught, so is equal to 1. So these will give you the stretches in terms of length, width, and thickness, or we call it height. Okay, so lambda 1, lambda 2, lambda 3. Lambda 1 in axial direction, that is length direction, lambda 2 is width, and lambda 3 is height or thickness direction. So this is one property that we get. And we know that we assume that width and thickness are same, so we have lambda 2 is equal to lambda 3. So if we replace that here, also we assume that lambda 1 is lambda, so lambda is a stretch. Okay, so when we replace lambda 1 is equal to lambda here, and lambda 2 is equal to lambda 3, so what we get, lambda 2 square is equal to 1 upon lambda, and when we take the root, what we get, lambda 2 is equal to lambda 3 is equal to 1 upon root lambda. So this is the condition for uniaxial tension test, okay, for incompressible hyperelastic material. So if we have given the axial strain or axial stretch, okay, that is the stretch in the lengthwise direction, and let's say value is 2, okay, so we can directly use that lambda 1, okay. But if you want to calculate the lateral, how we going to calculate the lateral, just we put in this formula. Let's say we put 2 here and we simplify, so we get the lateral stretches. In numerical, sometime what I will do, I said that axial stretch is that much, so lambda 1 is lambda, okay, but sometime I'll give you lateral stretch. So when you lateral stretch is given, that is lambda 2 lambda 3, so we need to determine lambda, okay. Now stress determination for hyperelastic materials. Now Hall-Zepfel in 2000 gives a relationship for determining stress for hyperelastic materials in terms of strain energy function W as follows. Okay, before going to the into the detail, just there are many type of equations there that will be used for determining the stresses. Why? Because the strain energy function W can be of three types, mainly micromechanical, invariant based, and stretch based. Hall-Zepfel basically gives us the, you can see, I1 and I2, that is stretch based material model. So means this formula is only valid for stretch based strain energy function, in which material model W is given in terms of stretches, okay, or stretch, okay. I1 is the stretch, the first invariant, second I2 is the second strain invariant, okay, and I3 is the third strain invariant, but not present in this formula. So this is only applicable to number one, stretch based strain energy function, and I1 and I2, okay. If I3 is present, then this formula will not entertain the third invariant. अच्छा, new Hickian material model. This is the first example of material model. I have defined there are different type of material models and they have a huge range. So out of that, just first I select new Hickian material model. So for new Hickian material model, strain energy function is given by, that is W is given by G upon 2 I1 minus 3. What is G? G is shear modulus. I1 is the strain invariance. Okay, the first strain invariant. So W is equal to G upon 2 I1 minus 3. Now if we want to determine the stress from this strain energy function, what we have to do? We have to replace this W equation in this above equation. That is, we have to replace W here, and we have to differentiate and simplify. So when we put this expression here, so what we get, G upon 2 I1 minus 3, and here G1 G by 2 I1 minus 3, since it is partially differentiated by I2, so I2 is not present in this formula, so this will be 0. And when we differentiate this with respect to I1, what we get? G upon 2. Okay, so the expression from this we get G upon 2. Okay, so when G by 2 multiply with this, so 2 will be cancelled and we get G lambda square minus 1 upon lambda. And lambda is basically axial stretch. So hence stress function can be determined by substituting W in sigma equation. Okay, so sigma is equal to G lambda square minus 1 upon lambda, and I have explained the method that how we are going to get this sigma. We got this sigma using this expression. Okay, putting strain energy equation in sigma equation and simplifying, we got sigma is equal to G lambda square minus 1 upon lambda. Above expression shows that shear modulus and stretch value is required to determine the stress generated due to uniaxial tensile load. Okay, so lambda is generally axial strain. Okay, now second material model that I choose is Monet-Rivlin material model. So for Monet-Rivlin material model, strain energy density function is given by C1 I1 minus 3 plus C2 I2 minus 3. Okay, now C1 and C2 are the coefficients that are dependent on the material property, generally on the shear modulus, and by using the material property we can determine the C1 and C2. Okay, so hence stress function can be determined by substituting W in sigma equation. So if we replace that in the previous sigma equation and simplify, so we get C1 for the first differential, and we got C2 for the second differential. And when we replace that in the previous equation, what we get? Sigma is equal to 2 lambda square minus 1 upon lambda. It is present there. And for this differential, we get C1 plus 1 upon lambda is present in the formula, and we get C2. So these are the two, C1 and C2. So in order to determine the stress, we need stretch and the coefficients that we have. Okay. Above expression shows that two constants and stretch value is required to determine the stress generated due to uniaxial tensile load. Note that constants C1 and C2 are determined using shear modulus. For solving numericals, values of these constants will be given. So if I will give any numerical based on Monet-Rivlin, so I will give you the value of C1 and C2. Okay, so that you have to directly use. Okay, in this expression. But for numerical purpose, uh, whenever you have to determine the stresses in any material model like Newton and Monet-Rivlin, what you will do, you first write strain energy function, then you write the Holmes-Zepfel formula, and then you show differentiation, and then basically you derive this relationship. Okay, unless without that, the marks will be detected. Even it's not present in the given in the problem that you have to derive that, but you should drive that relationship. Okay, now looking at the last problem of the lecture. Now uniaxial tensile test is conducted on incompressible hyperelastic material. Rubber has average chain density value of 1.23 10^27 meter square kilogram second square per second square, and it is at room temperature, that is 300 Kelvin. If a stretch in uniaxial direction is found to be 2, so lambda is given is equal to 2. Determine the amount of stress produced using Newtonian material model. Now take K is equal to this 1.38 10 to the minus 23. Okay, so K Boltzmann constant is given, NC is given, T 300 Kelvin is given, and lambda 2 is given. So let's see the solution. First of all, we need to determine the shear modulus. We know that shear modulus is equal to NC KT. So just replace NC, K and T in this formula. We get uh, this expression. When we solve that expression, we get 5 megapascal. So G comes out to be 5 megapascal. Okay. Now this is the material property that we have determined using the chain density. Now we will use this G in order to determine the stress. Now since for Newtonian W is equal to G by 2 I1 minus 3, and Hall-Zapfel gives sigma is equal to 2 bracket lambda square minus 1 upon lambda dava W upon dava I1 plus 1 upon lambda dava W upon dava I2. So we replace W here and differentiate and simplify. So we get uh, this formula, sigma is equal to G lambda square minus 1 upon lambda. So now the stretch in uniaxial direction is also given, that is 2. So we replace 2 here and simplify, we get sigma. Now replacing the given data in above formula, we get sigma is equal to 5 10 to the power 6, 2 square minus 1 upon 2. When we simplify, we get 17.5 megapascal of stress. With this, basically the numerical is solved. The thing is, if it's not given in the problem, you have to drive the stress formula using the strain energy function. Number two, you also, if drive the relationship of lateral stretch with axial stretch, is also gives you extra points. Okay, gives you full mark in this problem. Since lateral stretch is not required, so no need to drive that relationship. Okay, just use directly the axial stretch. But if lateral stretch is given, so you must drive the relationship for lateral stretch that I have derived in the lecture, okay, in the previous slides. And then by using lateral stretch, you calculate the axial stretch and then solve the problem. Now, important to note, if lateral stretch is given, then we need to drive the relationship for lateral stretch in terms of axial stretch that I have already derived in the previous slides. So lambda 2 is equal to lambda 3 is equal to 1 upon root lambda. For this numerical, we need this lambda, not lambda 2, lambda 3. Okay. So for example, if lateral stretch of 1.5 is given, then axial stress, axial not stress, axial stretch basically is lambda 3 is equal to 1 upon lambda. So just put lambda 3 equal to 1.5 and solve for lambda. So we get lambda comes out to be 0.444. So now we put lambda is equal to 0.444 in this formula and simplify in order to determine the stress. So the difference between this type of numerical and previous numerical is that if axial load is given, you can directly use this formula. But if lateral stretch is given, you need to drive the relationship for lateral stretch, and then you have to calculate the axial stretch, and then you replace axial stretch in the previous stress formula, and then you will get the final stress. Okay, I hope you understand this. Okay, so this uh, topic completed. Okay, and course completed. Okay, so I hope you understand these nonlinear elasticity topic and different headings that we have discussed. So inshallah, in the upcoming live session, we'll try to discuss it uh, in more detail and try to address your queries if you have any. Okay, so till then, Allah Hafiz. Okay, and best of luck for the exams.